All right, let's work through some examples of where simple harmonic motion appears, and once we identify it, how we can say something interesting about what's going on. So just as a reminder, remember that the simple harmonic motion equation, differential equation looks like that, which when you see that, you will automatically know that x sub t is some constant cosine of omega naught t plus some phase angle. All right, so example 1. Right, we already kind of worked or motivated this last time. Right, box on a spring, frictionless surface. Let's put the origin where the spring is neither stretched nor compressed. Newton's laws, or if we solve it by, this is kind of a Newton law example. Says that the differential equation of motion in the horizontal direction is that, which we said is the same thing as x double dot plus k over m times x equals 0. That indeed looks like the simple harmonic motion equation. We say omega naught is k over omega naught squared is k over m. And I know then that the solution better look like a cosine of omega naught t plus some phi. And based on my initial conditions, I can figure out a and phi. In this case, we can ask ourselves, what does the amplitude tell us? We already said something about the period. We said the period of motion is 2 pi divided by omega naught in this case, which in this case is going to be 2 pi m over k, all in the square root. So if I were to ask things like, qualitatively, does the period increase when there is more mass or less mass? Well, in this case, it seems like the period increases when there's more mass. What's the physical picture of that? Well, you have more mass, which has more inertia. The spring has to kind of exert more of an oomph. You can imagine it's harder to get a bigger mass accelerating than a smaller mass. Kind of intuitively makes sense the period should increase. Similarly, is a stronger spring going to reduce the period? Indeed. K is in the denominator, the period is going to go down. A tighter spring is going to want to oscillate faster, back and forth. You can imagine the period is going to decrease as a result. And the amplitude doesn't play a role. It doesn't matter how far away, as long as the spring obeys Hooke's law, which is not true for general. In general, right, think of a slinky. You pull a slinky away a little bit, it does kind of restore itself and it kind of has a Hooke law type motion. Pull a slinky too far away, it starts to distort itself and it might not even go back to being a tight slinky at the end of the day. Physical springs usually have some sort of limit of where it stops obeying Hooke's law. But assuming that it obeys Hooke's law, we can write it down as such. We talked about how everything is conservative in this case, so we should ask ourselves, can I write down, for example, the potential energy of this box? Well, I know the potential energy is 1/2 kx squared. So in this case, it looks like the potential energy is 1/2 k a squared cosine squared of omega naught t plus phi. And what about the kinetic energy, which is 1/2 mv squared, or x dot squared? So I can take the first derivative, and then square everything, and that looks like it's going to be 1/2 m a squared omega naught squared sine squared of omega naught t plus phi. Such that if I add these two together and ask myself, what about the total energy, t plus u? Well, seems like there are some 1/2s. There's an a squared in both cases, but that's about it. Then there's the kinetic energy as an m omega naught squared. That's all multiplied by cosine squared omega naught t plus phi. And then there's a K on the top one, and that seems like it's it. Oops, that should have been a sine, not a cosine. Omega naught t plus phi. And I really would love if I could do sine squared plus cosine squared, but there's all these numbers out in front. Though, remember that omega naught in this case we said was the square root of k over m. So that omega naught squared is k over m without the square root, or that m omega naught squared is the same thing as k. Aha. So both those terms have the same constant out front. So let me write them both as k, and then I can pull the k out. Then the thing has the cosine squared plus the sine squared of the same thing. And so I can use the Pythagorean identity, and it looks like the total energy is just 1/2 k a squared. Let me recopy it. Total energy is 1/2 k a squared. It's a constant. That's not too surprising. We expected that to be the case. But it's good that the math kind of supports that it's a constant. But here's where the amplitude plays a role. The amplitude is connecting to the total energy of the system. Right, by connecting to the total energy of the system, and actually it's that the total energy is proportional to the amplitude squared. Right, there's an a squared in this case, which actually is a general result. Something you see a lot for linear systems with oscillatory motion, that the amplitude squared says something about the total energy of the entire system. What if I let the box hang vertically instead? K, M, but now there's another force at play. Everything is gravity. Or there's also gravity. I'm going to again put the origin where the spring is at its natural length. Which is no longer the same thing as the equilibrium position. In the horizontal case, where it wasn't stretched or compressed is also where the box would have been in equilibrium if we started at that spot, because there was only one force in town. Now there are two forces, and you can imagine, I really should invest in a spring, right? You can imagine here is where the rope is kind of not stretched or compressed, but then that is not the equilibrium position that this apple falls in. It stretches down a little bit. There is now a force being exerted by this. If you think of this as a bunch of stretchy springs, there is a force from the kind of spring here that is balancing what's going on with gravity. The equilibrium position is where those forces are in balance. Let's see if that naturally arises when we try to figure out the solution. Again, this is a Newton law problem where it looks like m, now I'm going to use y double dot. Let's let up be positive. Right, so up is the positive direction. It looks like in this case there's gravity, so negative mg, and then there's also k, negative ky. And again, not that the spring is pointing down, but that negative in front of the k is because it's opposite the displacement from the spring's equilibrium position, which is the origin. Right? Really it's y minus y naught, but y naught is 0 in this case. So if the origin is where the spring is not stretched or compressed, if the box goes down, then the spring is stretched and it wants to move the box back up. But it's below the origin, so y is negative, so that term on the right-hand side is overall positive. That force is pointing up. If the box is above the equilibrium position, y is positive, that term on the right is negative, and there's a force that's trying to push it back down. Always double check, do these little sanity checks. So then it looks like y double dot plus, when I rearrange, there's still a k, right? So it looks like it's k over m times y. But then it's equal to negative g instead of being equal to 0. So if the right-hand side was equal to 0, it would be identical to what was above, but it's actually equal to a constant. So we need to do the case where we find both the homogeneous solution and the particular solution. The homogeneous solution, again, it's the same simple harmonic motion equation, so I expect it to be omega naught t plus phi. Or again, omega naught is the square root of k over m again. But then I need to be clever and figure out a particular solution such that when I plug it in, I get negative g. But again, the fact that it's a constant makes my life a lot simpler. And notice that if I plug in negative mg divided by k, its second derivative is 0, so who cares? But when I multiply that by k over m, the k and the m's cancel, and I get negative g at the end. So that is the particular solution. So then it looks like the full solution is a cosine of omega naught t plus phi minus mg over k. So if I were to plot this, here's where y equals 0. Here's negative mg over k. That's just a constant, but then the other thing is a trig function, so it looks like it's going to do something, depending on my initial conditions, it's going to do something that might look like this. So it's not oscillating about 0, but it's oscillating about negative mg over k. And we could ask ourselves, is there any kind of physical meaning to this location, negative mg over k? What happens when y equals negative mg over k? Well, notice that if I go back to my differential equation, mg minus ky, if I plug in negative mg over k, that is when this entire right-hand side goes to 0. So negative mg over k, that is the position where the spring and gravity are in force balance. In this case, this is where the spring is not stretched, not in force balance, because when I let go, it goes down a little bit, but it does find a location where it's in force balance. And in this case, negative mg over k, then if I were to, from force balance here, kind of push it down a little bit, it would oscillate about that position, not where the spring is neither stretched nor compressed. So there is some physical meaning to this location. All right, this is where Fg equals F spring, or it's the equilibrium position for force balance. And it oscillates around that point instead. Gravity is still conservative. You can write down all the conservation equations as well. Same old thing. What about that simple pendulum? So simple in that it's a point particle of mass m with a massless rod of length L. We'll do a physical pendulum next. It's displaced by some angle, then it oscillates back and forth. What's going on? Well, there are two forces at play. There's some tension along the rod, and there's gravity pointing down. We could also do this as a Newton's law problem, but let's use polar coordinates instead. So in polar coordinates, the tension force looks like it's always along the radial direction. There's no tangential component in polar coordinates, and it's always towards the origin. And then the gravitational force does have two components. We've worked this out before. Why is it a negative sign for the tangential component? Because remember, this is the r hat direction, and then by the right-hand rule, this is the theta hat direction. So gravity has a component, let me go thinner. Gravity has a component that is pointing away from the origin and is in the opposite direction as the positive theta component. Okay, and then we have our good old polar coordinate acceleration, which then is r double dot minus r theta dot squared, r theta double dot plus 2 r dot theta dot. But if it's a pendulum, there are some geometric constraints. R is a constant in this case, and it's just equal to L. The length of the bob is always away from the origin, is always equal to L. So all the R derivatives vanish. So it looks like A in this case is then just negative R theta dot squared, R theta double dot. So then if I look at the theta direction, it looks like the mass of the bob times L theta double dot, because again R is just equal to L, equals no component from tension, then minus mg sine of theta. And so cancel out an m, divide by L, looks like theta dot plus g over L sine of theta equals 0. So if I were to solve this, I would get theta as a function of time, which could tell me the motion of the pendulum as it swings back and forth. Notice this is not the simple harmonic motion equation, because we need it not to be sine of theta, but just theta, if we want to use simple harmonic motion. So in general, not simple harmonic motion. It, of course, is oscillatory motion. You can solve this pretty easily on a computer, and you would get some curve that looks very close to being sinusoidal, but as it turns out, as you make the initial value of theta bigger and bigger and bigger, if I have a displacement that's, say, 45 degrees and let that swing, it does obviously oscillate back and forth, but its motion is not given by a simple trig function. When, however, theta is less than about 20 degrees or so the displacement from vertical is small, then to a good approximation, sine of theta is approximately giving you the same value as just theta. And again, think Taylor series. The first term of the Taylor series for sine is just theta, then the next term is a theta has a theta cubed in it. So as theta gets small, the cubes and the fifths and the seventh powers of theta all get very, very small, and the first term survives. So when you have small displacements, then you do get the theta dot plus g over L times theta equals 0 is the motion of the pendulum. This is the simple harmonic motion equation. Instead of x's, though, now we have thetas. So again, I notice that omega naught is the square root of g over L in this case, right? No k's or m's really. Makes sense, there's no springs, so I don't know why a k should ever appear. But there's now a g and an L, and that defines what we called omega naught. And I should be able to write theta as a function of time as a cosine of omega naught times t plus phi. Now let's suppose theta at 0 is some theta naught, and I release it from rest. So theta dot at 0 is 0. So this is the case where I displace it a little bit and release it from rest. Well, theta dot as a function of time looks like it's negative a omega naught sine of omega naught t plus phi. There should be an equal sign somewhere. So when I plug in my initial conditions, it looks like a cosine of phi would equal theta naught. And then negative a omega naught sine of phi better equal 0 from the two initial conditions. And again, omega naught is a number, square root of g over L, so that's non-zero. And the only way the second equation can be 0 is if a is 0, which would kill the entire thing. That would just be theta as a function of time equals 0. That doesn't make sense. It's impossible to then satisfy the first initial condition that way. So then this suggests then that sine of phi better be equal to 0, which suggests that phi itself equals 0. Cosine of 0 is 1, so then that suggests then that a equals theta naught. Note the amplitude is not a position, right? In this case, since we're solving for theta as a function of time, the amplitude itself has units of radians. It looks like theta as a function of time is theta naught cosine of omega times t. So it is simple harmonic motion. It's oscillatory, but more specifically, it's simple harmonic motion in this case. It has a period of 2 pi divided by omega naught, which is 2 pi root L over G. And again, does that make sense? Longer pendulum, it takes longer for it to get back to where it started. That kind of makes sense. So the longer it is, the farther that bob has to move. Stronger gravity, which is what's causing all this motion, makes the period smaller. And that kind of intuitively makes sense as well. What about a physical pendulum? So suppose I have a hoop. There's a nail here right at the top, and I put the hoop, on the nail. There's a line here that kind of goes through the center of mass of the hoop. Right, this being kind of the center of mass, that might be important. And then notice that in this case, it's kind of displaced by some angle theta, and the hoop itself, you imagine, if left on its own, would just oscillate back and forth. This is not a simple pendulum, but I could ask myself, is it still the case where this hoop is going to undergo simple harmonic motion in some way? I'm going to solve this using torque. I think of it in terms of angular momentum, but let's think of it in terms of torque. So since torques and angular momentums depend on my choice of origin, I'm going to put my origin at the nail. The convenient thing there is that then the torque from the nail equals 0 because it's located at the origin, and torque is R cross the force. So there's going to be no torque from the nail for this particular choice of origin, but there is going to be a torque from gravity, which this is a continuous system, but remember, for constant gravitational force, we can imagine as if everything was concentrated at the center of mass. So let's see, I need, I guess, one more variable here. We need to specify that the radius of this thing has radius capital R. So the hoop has radius R. So then if I do the torque, R cross F, my thumb points into the page. If I imagine the torque from this position, it's going to want to make the hoop rotate clockwise, which is the negative direction. So R times mg, but then there's a sine of the angle in between them if I think of the magnitude of these things, with the negative sign I've thrown in for the clocks' negative relationship. Really, I could say, rather than thinking of it, maybe I'll take this away and just think about that. I can think of this in terms of there's only one component of the torque, since the torque only points into the page, so I could call that the z direction, right, where x and y are in the plane of the page. So in the z direction, the torque points into the page, hence the negative sign. And it has magnitude given by their product times the sine of the angle between them. All right. And that's the only torque acting on the hoop. So I know the net torque in the z direction better than equal the rotational inertia of the hoop times the angular acceleration, or theta just double dot in this case. So I have an expression for the torque, but now I need an expression for the rotational inertia. And you could look on one of those tables and you can find for a hoop, the rotational inertia is just given as mr squared. But again, that is for the rotation axis through the center of mass. The rotation, that'd be, if this is the hoop, that'd be for a rotation axis that would be located here. However, the rotation axis is located here. It is parallel and displaced by a distance equal to the radius of the hoop. So we can use the parallel axis theorem. So it looks like it's going to be the initial, the center of mass rotational inertia times the total mass times the square of the displacement, which in this case actually is also the same thing as the center of mass rotational inertia. So it looks like the new rotational inertia is not mr squared, but it's 2mr squared. All right, so we got 2mr squared theta double dot equals this torque, negative mrg sine theta. And m cancels. One of the r's cancels. So it looks like I got 2r theta double dot plus g sine theta equals 0. Or I could divide through by 2r. So it looks like theta double dot g over 2r sine theta equals 0 is the equation of motion for a hoop oscillating around that nail. Again, not quite simple harmonic motion because it's sine of theta. But again, if theta is less than about 20 degrees or so, then this is approximately theta double dot plus g over 2r theta equals 0. Here's simple harmonic motion. Omega naught then looks like it's going to be the square root of g over 2r. And theta as a function of time is going to be some constant cosine of omega naught t plus phi. Which a and phi are determined based on your initial conditions. Again, what's the period? 2 pi divided by omega, which looks like it's going to be 2 pi times the square root of 2r over g. R is units of length, g is units of meters per second squared. So again, it all makes sense that that has units of time at the end of the day. But notice it's not just L over g, now it's 2r over g. There's no general expression for the period other than it's going to be the square root of a distance divided by g. What it looks like inside the square root, though, is going to depend on the exact physical shape of the pendulum. In this case, if it was a hoop, I could make it a rod plus a ball, a more physical looking pendulum like a grandfather clock pendulum or something like that. You can work those out on your own. They all will have different periods that are saying something about how the mass is distributed. But when theta is small enough, all of them should obey simple harmonic motion. Okay. One more. This one is graphical. Let's see, for some, suppose you're given a potential energy function that looks kind of like this, where the potential energy as a function of x is given by negative sine of x times e to the negative x over 2. So there's a sinusoidal component, but then there's that e to the negative x, so as x gets bigger, the entire thing kind of dies out. Technically, this is all negative. Really, this is where kind of x equals 0. or sorry, u equals 0. So if this is the potential energy, of course, I could figure out what the force is. The force then is negative, right, du by dx, because it's only 1d. It's really negative the gradient. If you wanted to figure out the force, I don't really care so much about the force right now, but of course, we shouldn't forget the stuff we've talked about. That is indeed the force. But I want to ask myself, I could imagine if I'm located, if I release an object that's really close to this little dip, you might imagine that it might oscillate back and forth along that valley. Is that motion, and 1 is about here, it's a little bit greater than 1. Is that motion, if I release the object close to that little cavity, is that motion simple harmonic motion? And if it is, can I perhaps approximate, for example, the value of the spring constant if it's simple harmonic motion? This isn't necessarily a spring, but if this is the general potential energy, you can imagine if I release an object near that trough, that it would oscillate back and forth. If it's simple harmonic motion, what's the period, what's the spring constant, all that fun stuff. Well, we can remember our results from energy in that the equilibrium points is where du by dx equals 0. So I could try to find that particular equilibrium point first. So du dx, note how this relates to the forces being 0. So du dx, too bad to take a derivative of as long as I'm careful. And then there's the, let's see, it's going to be sine of x over 2 e to the negative x over 2. I believe that's right. If we set that equal to 0 and solve for x, the exponential is never 0, so we can get rid of that. So this is also when sine of x over 2 minus cosine of x equals 0, or where sine of x equals 2 cosine of x. You actually need a calculator to do this. So this x, when you solve it, or you find the root of this expression, that this equilibrium position is 1.107, approximately 1.107. Let's assume everything's in SI, so meters, say. So given that position, we could ask, just as a review, is this a stable equilibrium point at that spot right beyond x equals 1? Well, remember, the equilibrium point is stable if the second derivative is positive at the equilibrium position. So take the second derivative of this expression, and jumping right to the answer, it's cosine of x e to the negative x over 2, and then there's plus, some terms end up combining, sine of x e to the negative x over 2. I could plug in x equals 1.107 to this expression, and this ends up being about 0.62 at x equals 1.107 meters. So that's greater than 0. This is indeed stable. Not too surprising, given that I could make a plot and see that it's one where it is indeed a valley versus a hill. So it's a stable equilibrium point. So I can imagine that if I'm sufficiently close to that equilibrium point, I can approximate this complex potential energy function. Let's scroll up and remind ourselves, negative sine of x e to the negative x over 2. I could write that as a Taylor series about the equilibrium point. About the equilibrium point, there will be a constant term and a first derivative and second derivative, yada, yada, yada. I know the first derivative term is going to vanish because it's an equilibrium point. I've just figured out the value of the second derivative as a positive number. Then if I wanted to, I could find the third, the fourth, the fifth derivative at those points. But again, if I'm sufficiently close to the equilibrium point, I know that x minus x sub e, right, for the equilibrium is going to be sufficiently small. And maybe I can get away with approximating the entire function as just the first few terms. All right, so this is u, evaluate x sub e, plus the first derivative, evaluate x sub e, times x minus x sub e, plus 1/2 the second derivative, evaluate x sub e, x minus x sub e squared, plus the higher order terms. We said at the equilibrium point this is 0. U sub e is just a constant. So it looks like about the equilibrium point, you can plug in numbers. It looks like it's negative 0.514 plus 1/2. We just said this was negative 0.62 x minus x sub e squared, plus the higher order terms. But again, if x is sufficiently close to x sub e, I'm going to say that this is a good enough approximation. That's a 2. There we go. So it looks like this is negative 0.514 plus 0.32 x minus x sub e squared is an approximation for the potential energy function. Some constant plus 0.32 times x minus x sub e squared. Of course, you can compare that to the one for a spring. For a spring, you expect this to be 1/2 k x minus x sub e squared. Now there's this overall constant added on. But again, who cares about overall constants? Because constants in potential energy don't mean anything, because it's only changes in potential energy that have any physical meaning. So that negative 0.514, that just means my reference point is different. I can always define my reference point such that that negative 0.514 goes away. But if I compare this to this, then I can make a connection between the 1/2 k and this 0.32. So it looks like in this case I'm saying that 1/2 k is negative 0.32, where that k in this case is 0.64 newtons per meter. So I have approximated, you might call it a quasi-spring constant, in that as long as I'm sufficiently zoomed in on this region here, I'm not too far away, I'm not releasing a ball up here, or heaven forbid, on the other side of this hump. But as long as I'm sufficiently close to that trough, the motion will oscillate back and forth, and I can approximate that motion as simple harmonic motion, oscillatory motion that has a quasi-spring constant of about 0.64 newtons per meter in this case. And again, I've done that by figuring out the potential energy near that equilibrium point, sufficiently close to that equilibrium point, and then comparing it to what do I expect for simple harmonic motion, where I know it's 1/2 k x squared. So then if I wanted to plug in numbers, right, if the mass I release by like V0 is just 1 kilogram, then I know what? Then I know omega naught, we said was square root of k over m. That ends up being about 0.0787 radians per second. Such then the period, which is 2 pi divided by omega, ends up being something like 7.97 seconds at the end of the day. So given this potential form, as long as you're sufficiently close to that trough, right, you would expect things to oscillate back and forth with a period of about 8 seconds in that case. So in that case, we've taken something that was not clearly not just negative kx, in terms of the force, but by analyzing motion sufficiently close to an equilibrium point where I would expect, because it's stable equilibrium, oscillatory motion, I saw that as long as you're near that point, you can approximate it as simple harmonic motion and get something like estimating the hypothetical spring constant in period around that area. You might try to do the same thing here as well. If you're sufficiently close to this location, do you get the same answer, or is it a different value of the quasi-spring constant in this case? Obviously, you can't do it here because that's an unstable point. Any small displacement will make you run away. So these are all examples of kind of oscillatory motion that took place without dampening. But it's not just kind of mechanical systems as well that have this. Right? Take a capacitor, which we call stores charge or you can think of it storing energy. And suppose it's attached to an inductor, which stores energy in a magnetic field instead, where a capacitor is storing energy in an electric field. If you had a circuit that was just the two, right, this is a simple LC circuit, you could, for example, apply Kirchhoff's laws, or loop rules as they're sometimes called, and figure out what is the differential equation for the amount of charge that is, say, on the inductor or the capacitor at any one time. Well, doing the loop rule by looking at the change in electric potential around that loop, right, you got the change in the potential from the inductor plus the change in the potential from the capacitor, and by the loop rule, that better add up to 0. The inductor, remember, is just the inductance times the derivative of the current, and then the potential for across the capacitor is the charge Q divided by the capacitance, and that equals 0. But the derivative of current is the derivative of charge over time, so the derivative of current, that is L Q double dot plus Q over C equals 0. Or it looks like the charge obeys a differential equation of Q double dot plus, it looks like 1 over LC Q equals 0 in this case, which, lo and behold, is the simple harmonic motion equation. You would expect the charge on the capacitor to oscillate back and forth, and then this is essentially a very simple version of an alternating current circuit. The current goes backwards and forwards from the capacitor to the inductor, back and forth. How long does it take? Well, again, you have your Q naught. Looks like now it's the square root of 1 over LC. The period is 2 pi divided by omega naught. If you had the inductance and the capacitance, you could figure out the period of this oscillatory motion. Now, to motivate what's coming next, in reality, circuits are never resistance-less. There's usually a little bit of resistance on the circuit as well, in which case, by the loop rule and taking the resistor as ohmic, where I can just write it as I times a constant R, right, this ends up being something like L Q double dot plus Ohm's law is I times R, so R times Q dot plus Q over C equals 0. And notice that you get something that, again, is a second order differential equation, but has this dampening term as well. So you might ask yourself, are you going to get oscillatory motion that maybe dampens out as time goes on? And so next module, we will consider adding in friction, which allows potentially for oscillatory motion, but maybe oscillatory motion that dies down over time. And then at the end, we'll consider what if we were also allow for an external driver to push on on the oscillator, like a person pushing a kid on a swing, right? You're constantly exerting a force. In that case, kind of sporadically, right? Every time the kid is at a certain position, there's a burst, an impulse, say, a force that is applied. Or maybe it's, you're driving through a wind tunnel, or it's a pendulum in a wind tunnel, right, where there's a constant force being applied over time. These are sorts of things we'll look at next.